Imagine a threat so complete, it wouldn't just end your life. It would erase the very possibility of life itself. This isn't a story about an asteroid or a distant supernova. This is something far more fundamental. It's a threat that comes from within the fabric of reality. It's a process that could start anywhere, at any moment, without any warning at all. It would travel at nearly the speed of light, rewriting the laws of physics as it expands. Everything we know, every atom in our bodies, every star in the sky, would be undone. The universe would not be destroyed in fire, but fundamentally changed into something utterly alien and inhospitable. This cosmic nightmare has a name. Physicists call it false vacuum decay. It sounds like something from science fiction, yet it emerges from our best understanding of reality. It is a direct consequence of quantum field theory and our knowledge of the Higgs boson. The idea is simple, but its implications are profound and terrifying. Our universe might not be in its most stable state. It could be perched precariously in a false state of low energy, like a ball resting in a small dip on a mountainside, when a much deeper valley lies below. A slight nudge is all it would take for the ball to start rolling down to its true, stable ground state. The trigger for this event could be a random quantum fluctuation. A tiny pocket of space could suddenly tunnel into this lower energy state. This would create a bubble of true vacuum. Inside this bubble, the rules of reality would be different. The properties of elementary particles like electrons would change. The properties of elementary particles like quarks would change. The forces that hold matter together might vanish or operate in completely new ways. This bubble would then expand outwards, consuming everything in its path. There would be no escape. The wall of the bubble, moving at almost the speed of light, would arrive before any information about its approach. Reality would simply pop. This is the ultimate intersection of dread and data. The concept isn't wild speculation. It is a genuine possibility being studied by physicists at the frontiers of science. The ingredients for this scenario are all part of the standard model of particle physics, our most successful theory of the subatomic world. The stability of our universe depends on the precise values of fundamental constants of nature, numbers we have measured in experiments. We will explore this possibility not to create fear, but to understand the deep and sometimes unsettling nature of the cosmos. This is a story about the ultimate fragility of our existence, written in the language of physics. To understand this cosmic fragility, we must first journey into the world of the very small. We need to explore the fundamental building blocks of everything we see. Our tour will begin with the strange and beautiful concept of quantum fields. These are not just abstract mathematical ideas. According to modern physics, these fields are the most fundamental things that exist. They permeate all of space and time, forming the very fabric of the cosmos. Everything you see, the light hitting your screen, the chair you are sitting on, is made of these fields. They are the bedrock of our physical world, the stage on which all events unfold. Particles, the tiny bits of matter we learn about in school, are not the most basic components of reality. An electron is not a tiny, solid ball. Instead, it is a ripple, a localized vibration, an excitation in its corresponding field. The electron field, a photon, the particle of light, is a ripple in the electromagnetic field. Think of the universe as a vast, invisible ocean, composed of many overlapping fields. When you tap one of these fields with enough energy, a particle pops into existence, like a brief splash on the water's surface. This is a radical shift from our everyday intuition, but it is the world described by quantum field theory. This brings us to the vacuum. In classical thinking, a vacuum is just empty space. It is what you get when you remove all the particles and matter. But in quantum field theory, the vacuum is much more interesting. It is the lowest possible energy state of all the quantum fields combined. It is the calm, undisturbed sea. Even when there are no particles, no ripples, the fields themselves are still there. They are not empty. They are full of potential. The vacuum is a dynamic place, fizzing with quantum fluctuations and possibilities. Its properties define the very nature of our universe and the laws that govern it. In this documentary, we will make these abstract ideas tangible. We will use visual metaphors and thought experiments to build your intuition. We will visualize these quantum fields as vast landscapes of hills and valleys. The height of the landscape at any point represents the potential energy of the field. A ball rolling on this landscape represents the state of the universe. The lowest point in a valley is a vacuum state, a state of minimum energy. But what if the valley our universe is in isn't the lowest one? What if there's a deeper valley just over the next hill? This is the central question we must confront. The specific properties of our universe are not arbitrary. They are determined by the configuration of its fundamental fields. The precise values of these fields in their vacuum state set the rulebook for physics. They dictate the masses of elementary particles. They determine the strengths of the fundamental forces. For example, the reason an electron has the mass it does is because of how the electron field interacts with another, very special field that fills all of space. This field is known as the Higgs field. It is the key player in our story of cosmic stability, the ultimate arbiter of fate for the universe as we know it. We will explore a powerful concept called symmetry breaking. Symmetries are crucial in physics. They often lead to conservation laws and give our theories predictive power. However, many symmetries in the equations are not apparent in the world we observe. They are broken. Think of a pencil perfectly balanced on its tip. This state is symmetric. You can rotate it, and it looks the same. But it is unstable. The slightest disturbance will cause it to fall, pointing in one specific random direction. The symmetry is broken, and a particular outcome is chosen from many possibilities. The Higgs field performed a similar act of symmetry breaking in the early universe. In the hot, dense moments after the Big Bang, the fundamental forces were unified. As the universe cooled, the Higgs field fell into a specific vacuum state, much like the pencil falling over. This event, known as electroweak symmetry breaking, gave mass to many elementary particles and separated the electromagnetic and weak nuclear forces. The universe we inhabit today is a direct result of the Higgs field settling into its current value. Our existence is owed to this broken symmetry. This is where established science meets speculative but plausible extensions. We have measured the properties of the Higgs particle. These measurements allow physicists to reconstruct the Higgs energy landscape, its hills and valleys. The calculations based on the Higgs mass and other particles hint at a startling possibility. The valley our universe currently resides in might not be the true absolute minimum. It might be a false vacuum, a metastable state. This is the scientific basis for the nightmare scenario. We are on solid ground with our theories, but they lead us to a precarious cliff edge. Table of Contents. Part 2, Act 1. Quantum Fields and the Vacuum. About 6 sections. The fabric of reality ripples on a quantum ocean, the true nature of nothingness, the landscape of potential, the buzz of the void, the rules of the game. To truly grasp the precarious nature of our existence, we must first update our picture of the universe. Forget the old idea of tiny, solid particles moving through empty space. Modern physics paints a far stranger and more interconnected portrait of reality. The most fundamental things in our cosmos are not particles, but immense invisible entities called quantum fields. Imagine every point in space and time is permeated by these fields, like a vast, three-dimensional tapestry. There isn't just one field. There are many, all overlapping and coexisting everywhere. There is an electron field, a quark field, a photon field, and many others. These fields are the absolute bedrock of the physical world. This is not just a mathematical convenience. Quantum field theory is the most successful scientific framework ever developed. Its predictions have been tested and confirmed with astonishing accuracy. The fields are not in the universe. In a very real sense, they are the universe. They form the underlying substance of everything. The space between stars is not empty. It is filled with these fields. The space inside the atoms that make you up is also filled with these fields. They are the stage, the actors, and the script of the cosmic drama. Understanding this field-centric view is the first crucial step on our journey. It forces us to think of reality as a dynamic, continuous medium. The properties of this medium, the fields, dictate everything that can and does happen. If the properties of the fields themselves were to change, the fundamental nature of the universe would change with them. The laws of physics are emergent properties of the state of these fields. This is why a change in the fields could be so catastrophic. It wouldn't just rearrange the furniture, it would redesign the entire house. So, as we proceed, hold this image in your mind. A universe of vibrant, energetic fields filling all of existence. This is the arena where the battle for the universe's stability is fought. It is a silent, invisible conflict happening constantly, everywhere. The state of these fields determines our past, our present, and our potentially fragile future. They are the source of all matter, all forces, and all the light in the cosmos. But they also hold the potential for a complete and total transformation, a rewriting of reality itself from the ground up, starting from a single point in space. If the universe is made of fields, then what are particles? What is the electron in the wiring of your house, or the photon of light traveling from a distant star to your eye? In quantum field theory, particles are localized excitations of fields. They are ripples on the surface of a vast cosmic ocean. Visualize the electromagnetic field filling space. Add a discrete amount of energy at a point and a particle appears. We call that a photon. A photon is a focused vibration, a quantum of the field. Same for every particle. The electron field fills the universe. A ripple there is what we call an electron. The up quark field blankets the cosmos. A localized vibration there is an up quark. To make a particle, you must provide energy. EMC2. Mass is a form of energy. Particle accelerators like the LHC inject huge energy into a tiny volume. Fields vibrate wildly from the impact. New particles, new ripples, splash out from the collision point. Particles aren't permanent. They're transient manifestations of field energy. They can be created and destroyed. When an electron meets a positron, they vanish in a flash of light. In field terms, a ripple and anti-ripple cancel. Their energy transfers to the electromagnetic field as two photons. The fields themselves remain. Only excitations change. The ripple analogy shows mass and charge come from the field. The rules for how a field vibrates set particle properties. If a field's nature changed, every associated particle would change too. An electron might become heavier or lighter or simply cease to exist. Matter's identity is contingent on field states. Now we arrive at one of the most profound ideas in modern physics, the nature of the vacuum. If you were to take a box, remove every single particle of matter, remove every single particle of energy, what would be left? Our classical intuition says nothing, an empty void. But quantum field theory gives a radically different and far more interesting answer. The vacuum is not empty. It is the state where all the quantum fields are, in their lowest possible energy configuration. The ripples are gone, the sea is calm, yet the ocean itself remains. The vacuum is the universe in its ground state. This ground state is not absolute zero energy. Even in their calmest configuration, fields contain inherent energy. This is called vacuum energy, or zero-point energy. It's a consequence of the uncertainty principle, which forbids a field from being perfectly still and having zero energy. The vacuum is not placid and static. It is seething and dynamic, a fizzing foam of potential, with fields undergoing tiny, fleeting fluctuations. The nothing of the vacuum is a very complex something. These fluctuations have real, measurable effects. They can subtly alter electron energy levels in atoms, a phenomenon called the Lamb shift. They can create a force between two uncharged metal plates placed very close together, the Casimir effect. The vacuum constantly produces pairs of virtual particles. They pop into existence briefly and annihilate, borrowing energy from the void. The vacuum of space is alive with quantum activity, a hidden reality underpinning everything we see. The properties of the vacuum state are critically important. They are not an esoteric footnote. The vacuum's character defines our universe. The vacuum energy has massive cosmological implications, acting like dark energy that drives accelerated expansion. How fields settle into their vacuum determines the masses of particles and the strengths of the fundamental forces. The vacuum is not a passive background. It actively sets the rules for all physics. To better visualize the behavior of quantum fields and their vacuum states, physicists use a powerful analogy: the potential energy landscape. Imagine a field is like a ball that can roll across a vast landscape filled with hills and valleys. The ball's horizontal position represents the field's value. The height of the landscape represents the potential energy. The ball will naturally try to settle in the lowest possible position, where its potential energy is at a minimum. Those valley bottoms correspond to vacuum states. A field's vacuum value doesn't have to be zero. The lowest point might be at a non-zero field value. The Higgs field, for example, has a non-zero value everywhere. Its valley floor isn't at zero. The universe minimizes energy by having the Higgs on everywhere. This gives fundamental particles their mass. They constantly interact with the background Higgs field, and that interaction appears as inertia. The landscape can be complex, not a single bowl. It could have multiple valleys of different depths. The global minimum is the deepest valley in the whole landscape. A system there is in a truly stable vacuum. Local minima are shallower valleys higher up. A ball in one is stable against small pushes, but it's not the most stable state possible. This is the core of the false vacuum idea. A universe in a false vacuum sits in a local minimum, not the global one. Like a ball in a small dip on a mountainside, unaware that a vast, deep canyon lies below. Our universe looks stable, but that could be temporary. Metastable means stable for now, but not forever. There is a lower, more stable energy state out there. All it needs is a big enough push to get over the hill and begin the catastrophic fall into the true vacuum. Section 5. The buzz of the void. The vacuum is not perfectly quiet. Even in its ground state, a quantum field is subject to fluctuations. This is a direct result of the Heisenberg uncertainty principle, a cornerstone of quantum mechanics. The principle states that you cannot simultaneously know both the exact value of a field and its rate of change. This inherent uncertainty means the field's value is always jiggling slightly around its minimum energy point. Think of our ball in the valley. It's not perfectly still. It's constantly trembling. The vacuum of space is buzzing with this quantum jitter, a low-level hum of energy that permeates the cosmos. Most of these fluctuations are tiny and insignificant. They represent the creation and annihilation of virtual particles. They exist for such a short time that they cannot be directly observed. They are like tiny, fleeting bubbles in a pot of simmering water. They appear and disappear without consequence. However, quantum mechanics allows for a much rarer and more dramatic type of fluctuation. It is possible, though extraordinarily unlikely, for a very large, random fluctuation to occur. This would be like the simmering water suddenly throwing up a huge bubble, a violent burp of energy. In the context of our energy landscape, this means there is a non-zero chance that a small region of the field could get a kick big enough to push it over the energy barrier separating the false vacuum from the true vacuum. This process is called quantum tunneling. The ball doesn't need enough energy to classically roll over the hill. It can, in a sense, cheat. It can disappear from the false vacuum valley and reappear on the other side of the hill, in the true vacuum valley. It's as if a prisoner could suddenly find themselves outside their cell without ever passing through the walls. This tunneling event is the trigger. If it were to happen anywhere in the universe, a small bubble of true vacuum would form. This bubble would be a region of space where the fields have settled into their ultimate ground state. Inside this bubble, the potential energy would be much lower. The very fabric of reality would have a different configuration. This bubble would not remain small. Because it represents a more energetically favorable state, it would be driven to expand outwards in all directions, converting the false vacuum of our universe into the true vacuum as it goes. The buzz of the void contains the seed of its own potential destruction. Section 6. The rules of the game. The specific configuration of the vacuum is not just an abstract number. It is the master architect of physical law. The properties of the vacuum state directly determine the fundamental constants of nature that we measure in our experiments. These constants are the rules of the game for our universe. The mass of the electron, the strength of the electromagnetic force, constants that govern the strong nuclear forces, constants that govern the weak nuclear forces. These numbers appear arbitrary, but they are a direct consequence of the values the quantum fields have taken in our particular vacuum. For example, the mass of the W boson is determined by how strongly it interacts with the Higgs field's background value. For example, the mass of the Z boson is determined by how strongly it interacts with the Higgs field's background value. If the Higgs field's vacuum value were different, the masses of these particles would be different. This would profoundly change the nature of the weak force. Nuclear fusion in stars, like our Sun, depends sensitively on the strength of the weak force. Stars might not ignite, they might burn out in an instant. The universe would be a dark and sterile place. Quarks, electrons. If a false vacuum decay event occurred and the universe transitioned to a new, true vacuum, the value of the Higgs field would change. This would instantly alter the masses of all fundamental particles. An electron might become as heavy as a proton, or it might become massless. The quarks that make up protons and neutrons could change their properties so drastically that atomic nuclei would immediately fall apart. Chemistry as we know it, which depends on the stable structure of atoms, would become impossible. Therefore, a shift in the vacuum state is not a subtle change. It is a complete and total rewriting of the rulebook of reality. The constants of nature are not immutable. They are contingent on the specific vacuum our universe happens to occupy. If we are indeed living in a false vacuum, then the laws of physics we have so carefully discovered are themselves temporary. They hold true only as long as our universe remains in its metastable state. The transition to a true vacuum would not just destroy existing structures. It would erase the very laws that allowed those structures to form in the first place, replacing them with a new and likely far more chaotic physics. Wow.